Excel XPS and XAS simulation tutorials. This is a brief introduction of Excel macro program for XPS and XAS spectral simulation. Excel application almost every computer in your PC or user's PC available, and beamline developed the macro program for users to analyze the data even in the simulation. So in this tutorial, I would like to show you how we can simulate the spectra of the XPS and XAS at soft X-ray beamline. So this Excel, we already installed the macro here. You can run immediately from the macro menu, or you can set the shortcut key to run the macro more easily. So first of all, you can type simulation here. So at A1 cell, and you can run from the macro menu or shortcut key. If you have no saved data, the Excel asks you to save the workbook first. So this is the parameter we want to discuss in this video. Now the simulation mode is XPS. If we want to use the XAS simulation, we just change here. Now we use XPS. And photo energy, excitation energy we can specify here, which can vary from the beamline monochromator. So you can set any photo energy in your beamline. So you can actually set any value in the range of your beamline specification. Or if you are standalone XPS system, you can put the photo energy of magnesium K alpha or aluminum K alpha in the soft X-ray range only here. Work function, the charging factor here also available, but you can ignore in the first place. And the kinetic energy range you can specify for the spectral simulation with step size. So the maximum kinetic energy you measure is also limited by photo energy, so this value should be corresponding. The next step, we can explain simply here. For the fluids have maximum of photoemission peak and OJ peak appear in the spectra together. The ratio of the XPS and OJ spectra intensity also can be set. The secondary electron background we can influence greatly in the soft X-ray range, so we can simulate this secondary electron background by log normal function. So the parameter you can also set. The next step, you can also run again in the similar thing. So this is the atomic element you want to simulate, something like carbon, oxygen, titanium in this case. So you can the macro produce after the run the macro, the simulation worksheet that contains the raw data of kinetic energy and intensity of the simulation. The next worksheet produce the graph sheet plot of the spectra we can simulate from the calc, simulate graph, and the graph sheet plot the binding energy scale spectra at the top. In the bottom, you can also see the kinetic energy scale plot in the spectra simulated. And the kinetic energy scale, you can easily check the energy range you want to specify for the narrow scan of the spectra during the experiment. However, it's normally you use to see the XPS spectra in the binding energy scale in the journal publication. So you may see the titanium, oxygen 1s, carbon 1s peaks appears as the photoemission spectra. However, you can also see the OJ spectra, carbon KLM, titanium LM, OGKRA spectra also appears at the constant kinetic energy, but the photon emission peak appears at constant binding energy scale. So sometimes the OG peak and photon emission peak overlap together at certain photon energy. So you can choose the proper photon energy to see your interested peak clearly separate from the other peaks. You can also increase the photon energy like 900 eV. So the maximum kinetic energy also increased to 900 eV. You can also set the lowest kinetic energy here. So you can also run or shortcut key. So in the similar, just OK. So as you can see that the OJ peak becomes overlapping with the photon emission peak, so it is difficult to distinguish these titanium peaks in this area. But sometimes carbon 1s is more clearly separate from the other peak. So 900 is the photon energy. Photon energy is increased, and photon excitation ionization cross section also decreased. So the peak intensity is reduced compared with those appear in 650 eV photon energy. However, 900 eV is great advantage to see the fluorine peaks, because fluorine peaks binding energy is 700 eV. If you want to see the fluorine 1s, you have to choose higher photon energy than 700 eV. Then you can check the all element you are interested in. You can also change the atomic ratio. Something like oxygen is double of titanium. So the oxygen peak here is higher, the double of the previous peak that we simulate in. So for example, this is about 20 in the relative scale. You can reduce this number. So expect to see the just 10 intensity difference above the background here. So you will check many peaks in the XPS spectrum, and if you have a aluminum K alpha another source, laboratory source, you can put 1486.6 eV. And this the maximum kinetic energy have to also increase to that number. Then you can start the macro program here. You can clearly separate all the photon emission peak at the binding energy is similar to the other spectra we simulated previously, but the OJ peak shift higher binding energy. That means lower kinetic energy. It's a constant kinetic energy, and the binding energy of the photon emission peak also constant, so both of them are clearly separate. That the great advantage for the aluminum K alpha source. For most of the photon emission peak can be clearly separated in the periodic table. So if you want to change the mode of the simulation to X-ray absorption mode, the photon energy parameter doesn't matter here. So you can just only concentrate on the energy range here, change to the photon energy, and just run. So you can check the X-ray absorption peak appeared in the photon energy scale. In the second bottom, you can also see the differential spectrum. So you can check the peak differential peak position in the spectra of X-ray absorption. So you can see all the elements, and you can check which photo energy you have to scan for the X-ray absorption spectrum simulation. So this is very brief introduction of the X-ray macro, XPS macro, Excel XPS and X-ray absorption data analysis simulation macro. So thank you for watching this video.